Right, welcome back folks to the third part of this, the third lecture on experimental design and analysis in the core skills module. And in the final part of this lecture, we're going to look at this distinction between observational studies and experimental studies and kind of look at the pros and cons so that you can understand that when you're thinking about experimental design, because this is often one of the very first decisions you have to make when you're planning a study. So it's pretty easy to sum up the sort of general pros and cons of observations versus experiments. Observations are, by definition, typically much easier, cheaper, quicker to achieve than experimental manipulations. And that's because in order to manipulate a system, to intervene in a system, that typically requires resource. And in order to control every other variable, to hold things constant while you manipulate things, typically requires you to have systems under tight control. So in my field it would be probably laboratory experiments rather than field observations. If you're working in human health, it would be might involve sort of ethical clearance for interventions in human health, drugs and other treatments, which are very complex to arrange, as opposed to merely measuring some vital signs and observing what's happening to the body. So that's a key distinction, which is in favour of observation. So it's easy to get going basically and get started. And another major advantage of observational studies is that they tend to be realistic in the sense that they tell you what's going on under real conditions. In experimental situations where you manipulate variables, there's always the risk that you choose unrealistic situations or unrealistic values for the parameters that you're changing. So we looked at ceiling and floor effects earlier on, for example, which are a real problem potentially in experimental studies. Essentially, experiments are by definition artificial, as well as being expensive and time consuming, which might make you think, well, what's the point in ever doing an experiment? And the answer, I'm trying to remember why I've got a picture of cigarettes on this slide, but I can't for the life of me remember. I'm sure there was some simple example I was going to give, but I can't remember what it was. Anyway, one other disadvantage of experimental studies is this idea that we saw earlier on when we were looking at confounding effects, that you can get an inappropriate or unexpected effect of the manipulation that you were doing. So if when you manipulate one variable by mistake you manipulate other variables, that can obviously create significant problems and potentially even lead to completely inappropriate conclusions from a study. Yeah, so given all of that, why would you ever bother to do an experiment? And I think the answer may be obvious. The critical thing is that in order to make inferences about cause and effect, about which variables cause other variables to change, we really need to do an experiment. Because merely by observing that two variables are related, it doesn't tell us which variable caused the other to change, or indeed if there are confounding effects invisible in the background which are causing the relationship to happen. Whereas with an experiment, we're holding everything constant by definition and manipulating only the thing of interest. So when we see a response in the system, it must be caused by the manipulation that we've made, assuming we've designed the experiment appropriately. So in general, in experiments, if they're well designed, you're much less likely to have problems with confounding effects, and you will understand much more about causation, the pattern of cause and effect. And this is perhaps easiest to understand in the context of an example. So let's imagine that we're interested in the possible association between antibiotics and asthma. So it has been suggested, there's this general hygiene hypothesis, the idea that a lot of modern allergies are caused by the fact that we live in very clean environments with very few pathogens and parasites. And the absence of those pathogens and parasites in sort of ordinary life, kids getting mucky and swallowing all kinds of germs and worms and things, the absence of those pathogens and parasites might in some way be causing the immune system to malfunction, so that we end up with later in life allergies, including asthma. So one sort of component of that hypothesis is perhaps that the use of modern antibiotics very frequently in some parts of the world and in some conditions, which sort of tend to be broad spectrum and kill a whole range of different bacteria in your body, might be undermining the ability of the immune system to work properly. Maybe people who have taken antibiotics regularly are more likely to have asthma. So you might have this hypothesis that there's a causal relationship, that taking antibiotics regularly causes you to have asthma. So you might go out there and do a study and record. You could do a survey, an observational study, where you record whether people have asthma or not, and how many times they've used antibiotics in their life or in the recent period. And this would be observational because you're not manipulating anything, you're just observing the human population as it stands and looking for a relationship. And hey presto, let's say we find a positive relationship. People who have used antibiotics more heavily seem to be more likely to have asthma. Great, we think we found what we predicted, and therefore you might say we found support for our hygiene hypothesis. However, there are alternative explanations for the pattern that we've observed, different patterns of causation. So for example, there might be a sort of confounding effect here. There might be a third variable which is responsible both for asthma and for people taking antibiotics. So for example, it might be that people who have a long-term lung infection or are for some reason prone to lung infections have to take antibiotics to try to cope with that illness. And then taking it, and at the same time, sorry, that disease, that bacterial infection of the lungs, is also triggering asthma. So people are taking antibiotics because they've got bugs in their lungs, and they're getting asthma because they've got bugs in their lungs. The cause, the shared causal variable here, is the infection, and there is no direct causal relationship between the antibiotics and the asthma. So here, in our observational study, if we weren't recording the presence of these infections, we would be completely oblivious to the confounding effect of the lung infection in this relationship. And in fact, the conclusion we had reached about the hygiene hypothesis could be entirely wrong. And it gets worse, because actually there's a third pattern of cause and effect here that could be at play, and that is the idea that having asthma might lead you to be prone to infections, which means that you need to take antibiotics. So people who have asthma may have taken antibiotics more regularly because of the asthma. We all know that asthma is a fairly debilitating condition under certain conditions. It means that you can't clear your lungs properly, or that you have problems with restricted airways, and that could easily be associated with certain kinds of bacterial infection, I guess. I'm not a medical expert, but it's possible. And if that's true, then you might be going to the doctor every now and again to say, look, I've got another lung infection, I need to be treated with antibiotics. So our observational study spots a pattern, but that pattern, it turns out, and this is true of any observational study really, turns out it could be explained in three ways. Three patterns of causation. Either A causes B to change, or B causes A to change, or some other variable, C, causes both A and B to change. And unfortunately, an observational study will never allow you to tease that apart. It's only an experiment that will make this possible. And this issue, that observational studies can't identify causality, lies at the heart of a lot of problems that we have with the interpretation of science, both in the scientific community and more broadly in society. So under normal circumstances, under no circumstances would I recommend that you read the Daily Mail. It is a perfidious and deeply unpleasant publication in my view. Anyway, but it's great fun if you want to find some spurious stories, particularly about human health, often based on incorrect inferences from correlative observational studies. So I've got on screen here an absolutely classic example. You know, the headline was really how using Facebook could raise your risk of cancer. And this is based on a study which showed that people who used social networking sites like Facebook a lot seemed to be at elevated risk of cancer. And you look at those data and you think, really? Is the explanation that Facebook is giving people cancer? Well, of course, it's possible. You know, maybe being close to your phone for long periods exposes you to small amounts of radiation which give you cancer. It seems a bit unlikely. Maybe the kind of stress and anxiety brought on by social interactions on Facebook causes you to develop cancer. Again, seems pretty unlikely. Are there more likely explanations based on this observational study? Yes. So, for example, people who have cancer might tend to be stuck indoors, unable to get involved in other kinds of social activity, and so are more heavy users of social media as a result. So maybe cancer causes Facebook rather than the other way around. Some people would argue Facebook is a cancer, but that's a separate issue. And of course, there's a much more compelling third explanation, which is that there's a shared cause here, that people who have cancer and who use social media a lot share something in common. What that is, I don't know, but obvious explanations are that it's something to do with socio-economic situation. People who are, have poor diets, from poorly educated backgrounds, low income, tend to be more prone to certain kinds of cancer, and perhaps are it makes it sound like a negative thing, but tend to use social media more for whatever reason because of their sort of demography. We don't want to speculate on that. The key point is that there are 3 causal explanations for this relationship that the Daily Mail is reporting, and the one that it's got in its headline, which is that Facebook raises the risk of cancer, is the least likely explanation. And this is absolutely classic of the Daily Mail. Don't go and buy one because you'll add to their profits. But if you manage to sneak a peek at the Daily Mail, I bet you'll find a medical story like this somewhere in the pages of every edition. They just love them. Anyway, and just to prove how idea, it's a serious lesson actually. It's not just the Daily Mail. You will see all over the media and in serious scientific publications people making dodgy inferences from observational studies. And for this reason, if you have the choice going into a scientific study between an observation and an experiment, overall, on average, it's more informative to do an experiment than it is to do an observational study. But having said that, as we've seen, there are lots of reasons why you would do an observational study, and in general, if you look at the pattern, the way that scientific research develops, it tends to start with observations, spotting patterns, then we generate explanations for those patterns, and then perhaps at some later point we do an experimental study to establish whether there really are causal relationships underlying the patterns that we've seen. So if you've got the opportunity to do a realistic experiment that's feasible, financially and logistically possible, then it's probably the best option. Okay, so that's the end of this lecture. In the next lecture I'll be talking about statistical probability. So we're going to move on from experimental design now to really thinking about what we do when we've got data, how we make inferences from data, and that's going to really centre on this idea of probability, and in particular the p-value, which is at the centre of most stats that you're ever going to do.